Now let's take a look at our Old Faithful data, and let's think about a sampling distribution for the sample slope. So let's treat the 222 data points as the population of eruption times of Old Faithful, where x equals the eruption duration and y equals the interval of time until the next eruption. So we had this regression equation. The predicted interval until the next eruption is 33.966 minutes plus 10.35826 minutes per additional minute of eruption time. So times the duration time. All right. So let's check and see what happens now if we take random samples of size 20 from this 222. So on StatCrunch, had the students, had all you class do this, and we got lots of different samples. And so, for example, this was one sample that I got. And if you compare this sample regression equation to the population, notice that here my slope was only 8.2 and my y-intercept was 43.8. If we compare the r and the r squared, my r and the r squared were actually fairly similar. R was 0.856 instead of 0.877, and r squared is 0.733 instead of 0.769. So those are actually very close. Now I had everybody in the class do several sample take several random samples of size 20 using StatCrunch and find the regression equation and record the slopes and the y-intercepts. And we collected the slopes. Didn't have time to collect the y-intercepts. It turns out the y-intercepts also would have very similar characteristics as the slopes. But we usually don't do inference for y-intercepts in AP Stats, so we'll just focus on the slopes. So let me introduce some symbols. Beta, it represents the population slope, and B represents the sample slope. So our usual practice of using the Greek letters for the population parameters and the English letters as representing the sample statistics. So what we want to find out is if the sample slope B is an unbiased estimator of the population slope beta. And remember that an unbiased estimator means that the mean of all the sample slopes would equal the population slope. So when we look at this, our population slope was 10.38, and when we look at all of our sample slopes, they seem to cluster quite nicely around about 10. So it looks very probable that the sample slope is an unbiased estimator of the population slope. We'll look at a larger sample of sample slopes in just a minute. Now, what about the spread? Okay, so when we talk about a sampling distribution, this is what it is a sampling distribution of sample slopes. We want to talk about center, shape, and spread. So it looks like the center is about the same as the population slope. It also looks like the data is fairly unimodal and symmetric, suggesting that it follows a normal model, or at least we hope so, or a T model. Remember, T model is similar to a normal model with slightly different spread. What about the spread? Well, when we talked about sample means, our sample mean was dependent on when we talked about sample means, the distribution of sample means centered around the true population mean, and its standard deviation was sigma divided by square root of n, or the population standard deviation divided by the square root of the sample size. But here we're dealing with two variables, so it would only make sense that the sigma, or the standard deviation of our sample slopes, would be dependent on two things. It would be dependent on the residuals, which is the variability in the y, and it also is dependent on the variability in the x, because we have two variables, as well as the square root of the sample size. So if we look at our data from StatCrunch, the standard deviation of the residuals for the entire population is this number right here. The standard deviation of the x values, the duration values, I got from doing some summary statistics on StatCrunch. That's this number here. And then the sample size is 20 because we're taking samples of size 20. So when we compute all this, we get 1.27. So how does that fit with the standard deviation of the slopes? Okay, so I have a program called Fathom, and in Fathom, to kind of change my window size here, so we kind of get this down where we can see it better. Okay, so in Fathom, I have, this has the 222 observations from the data that we had. This is a graph of the population of all the duration interval points. And then down here, we have a scatter plot of one sample of size 20. And what this allows me to do in this program is I can continually collect new samples and replace the existing samples. So notice how this graph is going to change as I sample. I'm going to get different samples of size 20. Okay, so they're all going to have slightly different slopes, slightly different y-intercepts, look a little bit different, but they're very similar in lots of ways. Okay, now what's happening is this graph right here, I'll move this over here, this graph right here then is collecting all of the sample slopes from all of the different samples that I've gathered here, and it's collected 1,000 different sample slopes and made a graph right here. So we're going to look at this graph a little more closely back on the smartboard file. Here is the population slope, and here is the standard deviation that we calculated here. So if we create a normal model with this mean and this standard deviation, notice it fits quite well with the distribution of sample slopes. So the distribution of sample slopes, like the distribution of sample proportions and the distribution of sample means, follows a model that is unimodal and symmetric with a particular standard deviation derived from the variability of the x and the y variables and the sample size in this case. So we are dealing now, when we do inference, we are going to be dealing with a t model. And we're dealing with a t model once again because we will have an unknown sigma. We'll have to use s. And so when we do inference, we will use the t model, but you can see how this is, the t model is based on a similar shape to the normal model. So why is it important that we know what the distribution of sample slopes look like? It's because when we do inference, we have to rely on a model to tell us the probability or the likelihood of something happening. Whether we're going to choose to reject the null hypothesis, it's whether how we calculate the margin of error for a confidence interval. It's based on a model, and in this case it is going to be based on the t model, the same model that we used for sample means.